what we were doing? What we were doing previously?
Rules.
Rules in probability. Rules in probability. So what were the basic rules? One was summation. Summation rule. I think mutually exclusive events. I think everyone understood what is mutually exclusive events.
Yes, sir.
Isn't it? So mutually exclusive event can be simply drawn by a Venn diagram of this. Okay, everyone. Students, so we'll continue. Mutually exclusive events can be basically drawn by this. The occurrence of one will exclude the occurrence of other. That was a mutually exclusive event. And the sum of all the probability was how much? Was how much? Was 1. That was called a normalization condition, I think. And those events which are not mutually exclusive are something which was given by this, isn't it? Indira?
Yes, sir.
I think that was the case, no? You had a box and particles can either go in either one of the two. That was a mutually exclusive. Now, if you had something which was like this, which was intersecting, this was the volume V1, this was a V2, and this was V12. So this was called what here? Mutually exclusive. Not mutually exclusive. So the probability of particle being in V12 was how much? The total probability of particle being in this volume was basically given by probability of V1 plus probability of V2, and you have to subtract what? Probability of V1, 2. Isn't it? You have to subtract this area, this volume, sorry. So the probability of basically A plus B in case of this event was given by probability of A plus probability of B minus probability of AB. I think it was clear till here. And corollary was also, I think, was clear.
Yes,
No or yes?
Yes, sir.
Okay. Okay, now
Yes,
joint
sir.
probability. Now a joint probability. This is basically a multiplication. And do you know and gate is similar to that one. Now first you have to learn about what? Statistically independent. Statistically independent or uncorrelated. Uncorrelated. Clear? What does this mean? Statistically independent or uncorrelated basically means what? What does this mean? The probability of occurrence of one does not affect the probability of occurrence of another. Clear?
Yes, sir.
The definition is so actually let's say we have this kind of thing. Okay, this was a volume V1 and V2. So now I will ask you, what is the probability of particle being found in of getting in this V1 and B getting in V2? Clear? Probability of A getting in V1 and probability of B getting in V2 is given by how much? product. Clear? Is given by probability, product of both the probability, P1 by P2. Is it clear?
Yes, sir.
It's just like this question. Now, if you toss a coin, okay, I will
No,
just
sir.
explain. You can either get head or tail. Clear? Is it clear?
Yes, sir.
If you toss it 2 times, you can either get head, tail, head, or tail. Is it okay? So what is
Yes,
the
sir.
probability of getting head in 2 times?
1/4.
Is basically
Yes,
1 by 4,
sir.
which is simply getting this and this. The probability of getting this is half, and the probability of getting this is half. So it's basically 1/4. Clear?
Yes, sir.
Occurrence of this does not affect the occurrence of this.
Yes, sir.
I think this must be clear, no?
Yes, sir.
Right.
Yes, sir.
Our probability of getting head tail is 1/4 again.
Yes, sir.
If you do it 3 times, again you will get the same thing. Clear? Should we try
Yes,
three
sir.
times? Should we try 3 times?
Yes, sir.
Okay, you can get head,
Yes, sir.
tail. Now tell me what more we can get. Head, tail, head.
Yes, sir.
Apart from
Tail,
that,
head, tail. Yes, sir.
tail, head.
Head, tail. Head.
I think it's done now for one.
Yes, sir.
Now second, we can start with tail, tail,
Tail,
no?
tail, tail.
Yeah.
Tail, head.
Tail, head. Okay. Then tail, head, tail.
Tail, head, tail.
Then
Head, tail.
head, tail. How much did we get? Probability of getting this is 1, 2, 3, 4, 5.
3, 4, 5,
Or do we
8.
have some more? Do we have some more? Is something left?
Mm.
1, 2, 3, 4, 5, 6, 7, 8. No. So the probability of getting head is, I think it's fine. Is how much? 1 by 8. No.
Yes, sir.
Favorable event is 1. So probability of each is head into probability of head into probability of head is how much? If you multiply this 3, half into half into half, how much you get? 1 by 8. No.
8. Yes, sir.
So this kind of things are called what? Mutually uncorrelated. Clear? Or statistically independent. I think
Yes,
it's
sir.
clear, no? I think I will give you one small.
Yes, sir.
1 by to the power n. Probability of getting any event is this much. Clear? N is the number of event, number of trials. You can also write in this manner. This is just writing. Clear? For 1 time it will be half. For 2 time it will be 1/4. Clear? For getting head, kind of thing.
Yes, sir.
So this kind of event are called uncorrelated. So I will give you one more example for correlated. Okay. Suppose you are supposed to, there is red ball. Let's make a red. I think now we can make red. One is you have red, 2 red balls and 1 blue ball. Clear? Probability of getting. Now these are not mutually, these are not statistically independent. Because if you take out this red ball, now what is the probability of getting red ball from here? From one pick. How many? There are 3. And how many favorable events are there? 2. So the probability of getting red ball is 2 by 3. Is it clear?
Yes, sir.
Now as soon as you pick one ball, now the probability changes. Now do you see?
Light
The
ball.
probability of getting one red is half and blue is also half. Clear?
Yes, sir.
So this kind of event are not what? Statistically independent. These are related events. Can you see? These are related events. Yeah, this is the difference between uncorrelated and correlated events. I think this must be clear, no? So I think we
Yes,
can
sir.
continue. Hi. Okay. Now, next is called conditional probability. Do you know what is conditional probability? Whatever I explained just now is your conditional probability. Clear? That red ball and blue ball. You have two blue ball and one red ball. This kind of things are called what? Conditional probability. Clear?
Yes, sir.
The probability for an event A to occur under the condition that the event B has occurred is called conditional probability. I will tell you one more. Probability for an event A to occur under the condition what? That P has occurred. Clear? And it is denoted by P A by B. And also it's given by P A by B is simply given by N of A B by B. Clear? Now you have this kind of event. There you have a common event which is NAB. This is NA. This is NA. This is NB. Clear?
Yes, sir.
Now the probability of event A to occur provided that B has occurred. B has occurred will be basically the intersecting part this divided by this one. Is it clear?
Yes, sir.
Let's do one example. I think after that it will be clear. Now let's say you have a box containing how many balls? 4 black and 3 white. Clear?
Yes, sir.
So what is the probability that at 2 successive draw the ball drawn are both black? So the question is, if we draw 2 times, if we draw how many times? 2 times. So what is the probability of getting 2 black balls in this succession? Clear? So total number of event is 4 plus 3,
7.
7. Okay. Number of favorable event is for one black to come at a first
Black 4 by
4 by
7.
7. I think it's correct, no?
Yes, sir.
Now the event, now this, as soon as you pick the black, now the probability changes. Do you see? Do you see? Now it will not change if you pick the black ball and again place it. Now you have picked the black ball. Now the number of balls left in the box is how many?
3.
3. Okay. 3 black and 3 white. Isn't it? The second ball therefore is selected from how many balls? Now the second
3.
ball is selected from 6
3
balls,
ball. 6. Yes, sir.
from total 6 balls. Hence the probability for this black ball to occur is how much?
3
Again
by 6.
3 by 6. Is it correct? No.
Yes, sir.
Yes or no? Because
Yes.
we have 3 number of black balls. So 3 divided by 6 half. Thus, the the occurrence of first event will what? Will affect the probability of getting the second event, isn't it?
Yes, sir.
Now this is affecting this. So the probability of the event A plus B or both black ball is basically given by probability of A times probability of
Yes,
B by A. Clear?
sir.
Which is basically given by 4 by 7 times of half, which is 2 by 7. Probability for both the black balls to occur. Clear? Basically, you multiply this two. This is your conditional probability, which is coming due to the occurrence of getting black ball that another. I think both I used BB. This also should be B. Should I use different? Should I use A for this one? So you won't get confused. This is for getting A and this is for getting. So the probability of getting what? B as the A has occurred. Clear? This is your joint probability divided by, there's no division. It's basically given by how much? It's given by
Probability of
4
A.
by 7 into 1 by 2. Basically 1 by 7. Clear?
Yes, sir.
I think this must be clear. I think this is how you use the conditional probability. Now continuous random variable. Till now what we have done? Till now we have done only discrete distribution. Have you seen? Or discrete random variables. The event which we have considered just now is here. Those are discrete because it was either head or tail or head kind of thing. No. And also for the dice, it was either event 1, 2 kind of thing. So this was kind of discrete event. Clear? Is it clear?
Yes, sir. Yes, sir. Yes, sir.
Now, what do you mean by continuous random variable? Now, basically, continuous random variables are those variables which take the which take the number continuously. Now, what does that mean? Now, if I ask you a question, the time taken for a driver or for a car to reach from from where? Gangtok to Tadung. The time taken by the car to reach from Gangtok to Tadung. Now it will be random, isn't it? It will be random. Sometimes he can take how many? 15 minutes. Sometimes he can take 14 minutes. Sometimes he can take 14.01. Sometimes he take 0.01. So on and so forth. He can take continuous number. Clear?
Yes, sir.
So this kind of event are called what? Continuous random variable. I think this must be clear.
Yes, sir.
So let's say we have a water. We have a water and let's consider a small element. This whole thing was what? Z, and we consider a small element dz. So what is the probability that the particle will end up over here in the small region dz? So one is obvious, your probability for the particle to be present at dz is proportional to what? The area of this or the length of this. The larger it is, the more probable it will be. Is it clear? Is this point clear or not?
No, sir.
So if we just increase the size of this, okay. Initially it was of this size. Now the probability of particle entering over here will be less. Over here will be more, isn't it? Because the area is larger.
Yes, sir.
Now if we keep on increasing the area, if we make the area sufficiently large, let's say till here, the whole area we consider, the probability will be 1. Clear?
Yes, sir.
So it will depend on this dz, isn't it? So the probability of particle entering in dz will depend on dz itself. Just like previously we have done this area, no? If we increase the size of the area, the probability also increases, isn't it?
Yes, sir.
So that's why it will depend on dz. So apart from that, you have a function which is called fz. This is your what? This is your what? Probability density. I think you have studied this. Where you have studied this? Probability density.
Quantum mechanics.
Yes, that is exactly this thing. This is your probability density. So usually to get the total probability, you used to integrate, no? I square dx kind of thing. This is the thing you used to do, no? Isn't
Yes,
it? So
Yes, sir.
I think when your z goes from 0 to z, what should be your total probability? It should be 1, no? This is your
Yes, sir.
normalizing condition, just like you have in here previously. That was your normalizing condition, no? Psi square, isn't it? It was your normalizing
Yes,
condition.
sir.
It was 1. So this is exactly this one. This is how your quantum mechanics and statisticals are related. Yeah,
Yes, sir.
it's not related, but the mathematics are related. The physics is like is different. Okay, now we have a question. Okay, let's do one example so it will be easier for you to understand. So what is the probability that the molecule in the cubical vessel, this is a cubical vessel, let's make it slightly better. Let's make it slightly fancier. So this is your cubical vessel. Yeah. So you consider a small volume, this just like previous one. This as what? dz. Clear? And the particle is randomly moving over here. Clear? In this manner, it can move anywhere, randomly moving over here. So the question is, what is the probability that the particle will lie inside this volume made by dz? Is it clear?
Yes, sir.
So the probability of particle being over there is basically what? Delta V by V. The volume which is made by dz is basically delta V, and total volume is how much?
V.
Is V. So it's basically delta V by V. I think that we have done so many times. Do you remember?
Yes, sir.
We have equally distributed this area and make a
Yes,
rectangle. So it will depend on a volume. I think that is clear. So delta
Yes, sir.
V is basically given by how much? Let the side of this cube be how much? A. Clear? Each side is how much? A.
V.
Basically, if you multiply area with dz, it will give you delta V, isn't it?
Yes, sir.
I think this much is clear. A square will give you this area, will give you this area, and if you just multiply by its height, it will give you what? The diagram is extremely bad. A square will give you this area, surface area, and if you simply increase by dz, it will give you what? Volume. So the volume delta V is given by this one. And the total volume is how much? A cube. Isn't it? Area of a cube. So it will be basically
Yes,
how much?
sir.
Dz by A. Now I think it's clear. So this is your continuous random
Yes, sir.
variable. Just wait. Now we are going to do what? Mean. I think mean we have already done in quantum mechanics itself. Do you know how do you find the mean? It's called mean or average, or what more can you call it? Expectation, mathematical expectation value, or something. Do you all remember?
Yes, sir.
How do you usually find a mean? Let's say we have 5 people, okay? Let's say we have 5 people. And what did we do? We group them with respect to their age. Yeah. Age 20, 21, and 15. Let's say 3 people ended out here, and 1 people ended out here, and 1 people. This is Mingma. Okay. Okay. Now, how many people are there?
5.
Now, if I ask you to find the mean, how do you usually find it?
3 divided by 5.
No.
No,
There
no.
are 20.
3 plus
There are 3 number of people who are having age of 20, and I'm asking you to find the average age. Okay. Number of people. Number of people, or this is also called a frequency. Let's not use that term. How do you find the average of age? What do you usually do? There are 3 people with 20, 20 plus
plus
20
divided by
plus 21 plus
plus
15
sorry,
divided by 5. There are total number
5.
of people are 5. This is how you do, no?
Yes, sir.
But simply what you can do is you can simply multiply this frequency by 3 into 20 plus there is only 1 people sitting out here
21 into 1
plus 15 divided by
into
total
1.
number divided by
5.
5. This is how much it will be 60 plus 21 plus
21 plus
15.
15.
How much it will give you? I don't know. 60, 70, 80, 90, 96 by
6 plus
5.
21 plus
How much you got?
2.
5, 5, 9, the 45.5. No. So this is the average.
19.2.
Actually, it shouldn't be. Is this the average age? Most
Yes,
probably.
sir.
Most probably.
19.2.
19.5. No, 19.2. Sorry. 19.2. Sorry.
Oh.
Sorry. 19.2 is exactly yeah.
Average.
So also similarly, how we can find this is, so total number of people is
5.
5. And how do you get the probability? 3 by 5 for this one, isn't it? From the
Yes,
frequency
sir.
for 20 number of age. It's extremely crowded. Let's do it somewhere over here. So probability for the age to be 20 is how much? 3 by 5,
3
isn't
by
it?
5.
Probability
Yes,
of getting 21 is 1 by 5.
1 by 5.
Probability of being age 15 is 1 by 5.
1 by 5.
This was the mean age. So similarly, what we can do is we can multiply the probability with age. Clear? Plus probability with age plus probability with age. How much it will give you? Similarly, 19.2. So how did you find the probability? Basically, how do you find the mean? Mean you are able to find the mean by simply doing what? Probability of getting a event into number, that number. Isn't it? This is how we defined the mean previously. This is always
Yes,
how you
sir.
used to define the mean in your quantum mechanics. Do you know? It was denoted by this, used to multiply with this, and n used to sit over here, and psi square used to, isn't it?
Yes, sir.
Psi star
Yes, sir.
x psi you used to do, no? Isn't it? This is how you used to do. And psi star psi, product of this is simply a probability. And x, which is sitting, you are finding, whatever you are finding, which will be sitting over here. Is it clear now?
Yes, sir. Yes, sir.
Mingma, clear? No, not clear.
Yes, sir.
Okay.
Answer clear.
Ekdam clear. Okay, very good. So the probability can be defined as what? Summation of probability of each i's into f of I. Clear? In general, you can write for any function in this manner. Clear? We have to sum over everything. I think you just saw it over here. We are summing over all the
Yes, sir.
quantity. Summing. So that's why you'll get a summation over here. Clear? Instead of number, sometimes you can have a function also. So that's why it's a function over here. This is a general form, which is very much related with the quantum mechanics. Clear? This is your general form. I think mean is also done. So how do you find the mean for a continuous variable? This was for discrete. For continuous, what do you do? Simply it's clear. Because probability of getting z was how much? F of z into dz. Do you remember?
Yes, sir.
For continuous, it was this one. So simply if you find for probability of getting z, or the mean of z is simply given by integration of probability of z. Integration of probability of z into probability of z. Z times the probability of z, which was integration of z f of z of dz. I think this must be clear.
Yes, sir.
This is your final expression. So this is how you find the mean for both discrete and continuous variable. Can I write slightly smaller? Will you be able to see? Or should I zoom it slightly?
Yes, sir.
No, variance. Variance or dispersion. Sometimes you want to know how much a particular value is away from the mean value. Let's say you have a certain kind of distribution. Let's say you want to know how much this point is far from the mean. Clear? From the mean value. This you can simply do by what? Taking the value of mean and subtracting it with that value. So delta n, you can simplify this delta n, let's say, you can simply find it by the value of n minus mean of n. Is it clear?
Yes, sir.
But actually this does not give you the full story. Actually we want we want to roughly know how much the value has dispersed or how they are distributed. Clear? How much they are scattered actually. So you take the mean of delta n. I think this we did it in quantum mechanics, so I'm just repeating over here. So which will be simply 0. Clear? So we need a new definition for this. So the new definition is basically given by what? Your variance or dispersion is given by variance or dispersion, which is basically given by what? Sigma square. Instead of taking this, what we do is we square this. Clear? And which will give you what? This is your variance. And your standard deviation is given by your deviation is given by what? By sigma. It's given by sigma. Variance is given by sigma square and standard deviation is given by this. Have you seen this somewhere?
Yes, sir.
Where?
Quantum mechanics.
Sir.
Yeah, Mingma, tell me.
So that sigma square, that square is both inside.
This square is inside. This square. This you are talking about. Mingma, you are talking about this square.
Yes, sir.
Yeah, this is the square. So after taking a square, no, what will happen is it will not be 0. Now let me tell you. Should we do one example? Let's do one quick example. Let's say 1, 2, 3, 4, 5. You have this number. What is the mean of this? This is your number. What is the mean?
1 plus 2 plus 3 plus
Basically 3.
4 plus...
It will give you 3. If you add all this, how much you will get? 3, 6, 10, 15. No, 15 divided by 5.
5.
So mean is 3. Is it clear? This is your sigma n. Clear? Now you want to find delta n. How far it is. Clear? So what you do? N minus mean of n. How much you will get? Let's start from this one. How much it will be? It will be minus 2. Similarly, another number will be minus 1. 3 minus 3 will be 0. Then it will be 1 and 2. Clear? Is it clear or not?
Yes, sir.
I think it's not clear. Let's do it one by one. Okay. Let's pick one number. Indira, let's pick your first number. Clear this one.
Yes, sir.
And we want to find how far it is from the mean value. We just subtract this. 1 minus 3 will give you how much? Minus 2.
Minus 2.
So let's check for the other number. For minus 2, how much it will be? 2 minus 3 will be minus 1. Clear?
Yes, sir.
Another number will be 3 minus 3 will be how much? 0.
0.
4 minus 3 will be 1.
1.
5 minus 2 will be
3.
2. Oh, yes, sorry. 3 is 2.
3. 2.
So now, if you take a mean of delta n, how much you will get? Because the distribution are minus 2, minus 1, 0, 1, and 2.
Minus 1, 0, 2.
Now, if you take a mean of delta n, how much you will get? Mean of this 0.
Yes, sir.
Because this will cancel out this will cancel out this is.
Cancel.
So that's why we cannot take this as a definition of. Clear?
Yes, sir.
Now, see what will happen if you square.
Yes, sir.
Now, if we square this number, what will happen? If we square this, minus 2 will be 4.
4.
This will be 1, 0. This will be
1.
This will be 4.
4.
So now it's what we are doing, taking a mean of n minus delta n whole square we are taking. Yeah.
Yes, sir.
This is n minus delta n. This is basically what? N minus mean of n's whole square, isn't it? This is the number distribution. Now, if you take a mean of this, Is this 0? No, because it's 4 plus 4 plus 1 plus 1 divided by 5. No, 8, 9, 10
Yes, sir.
is 2. Clear?
Yes, sir.
So this is why we are defining this into a new definition. Is it clear, Mingma, now?
Yes, sir.
So this is called your dispersion. It will tell you how far or how much of random number are dispersed. Okay, is it clear?
Yes, sir.
Whether the
Yes,
random
sir.
number has been dispersed all over the place, or is it concentrated to a single point kind of thing, will be given by what? Your variance. Clear? I think now that's why we are defining a new definition for this. I think that is also clear. Now this is defined given by a variance, and the square root will be given by a standard deviation. I think till now, I think it's clear. This you have done. This is your uncertainty in your quantum mechanical term. Now next is your probability distribution. Now what is the probability distribution? Now till now, have you noticed something? That whatever probability we did was, we considered that it is uniformly distributed, isn't it? The probability is uniformly distributed. The area was equal, same area, all the area was same. All the areas were same, isn't it? Do you remember?
Yes, sir.
This was a uniform distribution. No, actually this is not the case always. Some of the space is what has the probability of being there more, and some will have less. Just like in your quantum mechanics, do you remember? If you plot the what probability density psi square, you used to get this kind of thing. For a infinite potential well, you used to get this thing, yes or no?
Yes, sir.
So the probability of a particle being in this region is more as compared to particle being in this region, isn't it?
Yes, sir.
So is this uniformly distributed? No.
No.
Clear? So this kind of distribution are not uniformly distributed. So in this case, what do we use? We use weightage. For this reason, the weightage is more. For this reason, the weightage is
Less.
this weightage is less. For this weightage is more. For this weightage is less. So probability, we write the probability for this kind of distribution, which is not uniformly distributed, by dx by L. Clear? Now I will tell you. Suppose if it was uniformly distributed, and if the each area size was dx, let's say, or dA or dx, let's consider a line. Line is equally braked. We have an equal break in line which has a length of dx. So the particle being found in any one of this length is basically dx by total length, isn't it? Yes or no? I will explain it one more time if you want. Mingma,
Yes, sir.
did I explain it one more time?
Yes, sir.
Okay. Let's say you have a length, this kind of length. Clear? Total length, can you tell me what its total length? The total length, let's say it has a total length of L, and we break it into equal parts of length of dx. This is also dx. This is also just like a ruler, which is have a centimeter or millimeter kind of thing. No, we break it into a same kind of situation. Clear? Which has an equal length. So the probability of particle being in any one of this region which is bounded by this is what? Is length dx divided by total length. Is it correct? I
Yes,
think
sir.
this must be correct, no? So that's why, but let's say we break this length into different size. Clear? We break this into different size. Length is L. Let's say I break this into this one and this into smaller section, this into this into smaller section, so on and so forth. Clear? Now to govern this, the weightage over here is more, the particle is more probable over here as compared to this. Can you see? Because its length is longer. So that's why it should be dx by L multiplied by its weightage. That weightage will take care of how much the probability will be in each region. Is it clear now? Is it clear?
Yes, sir.
Am I lagging
Yes,
or
sir.
Mingma, is it clear? Indira, is it clear?
Yes, sir.
Yes, sir.
Okay. So that's why the new probability is given by simply this one. But usually we don't use weightage. Okay. And you know the normalizing condition, P of x of dx from 0 to L. If you take this, how much you'll get? You'll get 1, isn't it? The particle will, yeah, exactly end up in, should be in this length of y. So this is your normalizing condition. Total probability should be 1. Now, instead of weightage of this each probability, this is the weightage for each probability. Okay. For this, weightage is different, is more. For this, weightage is different. Instead of weightage, what do we use? We use a function. Clear? We use what? Distribution function. What do we use?
Distribution function.
Basically, distribution function. What tells you what is how the particle has been distributed in this region. So instead of taking weightage, what it's sufficient to take only the distribution function itself. Clear?
Yes, sir.
Can you tell me if we have this kind of wire? I'm asking to you too. As you go further, it's become even smaller. Okay, this length become even smaller. As you move this side, it's become larger and larger. Clear? It becomes like this. So what kind of distribution will there be? The particle will be distributed. Will it be distributed in this manner?
Yes, sir.
Will it be distributed in this manner? Yeah, obviously, no.
Yes, sir.
Because it will be having high probability over here and less probability as the area is or the length is keep on decreasing on this side. Is it clear?
Yes, sir.
Now this function we can define as what?
Yes, sir.
E to the power negative kx square Gaussian distribution. Yeah. Or we can define by some function. This is exponentially decaying on both sides, which we can simply write in this manner. Okay. Clear?
Yes, sir.
This is a Gaussian. If you plot this, you'll get this. So instead of considering the weightage, it's sufficient to just consider this function itself. Clear? Because this gives you a profile of this distribution itself. Can you see? Instead of taking care of weightage, let's
sir.
have weightage more here, weightage more here, weightage slightly less. Instead of doing that, what we can do is consider a distribution function, which is given by that. So the number of particle in the interval dx is f of x of dx. Is this point clear? The number of particles. The number of particles in the region is basically f of x of dx. So the total, this is obviously 1. Interval is dx is basically this one. So if you integrate over all, this will be basically n, not 1. How much it will be? It will be 1. I'm asking to you too. If we do this,
Yes,
will
sir.
it be 1? For dx, fx is a distribution function. If you multiply by dx, this is the number of particle in dx. Clear? Is this point clear till here?
Yes, sir.
So if we
Yes, sir.
integrate
Yes,
from
sir.
0 to L, f of x of dx, will it give 1? Will it give 1?
Yes, sir.
No, the
Yes, sir.
probability is 1. No, it will give you the total number of particles. No. Is this
How, sir?
Because this is a number of particle in dx. Clear? Now,
Yes,
if
sir.
we integrate over a whole length, then that will give you a total number of particles, isn't it? Yes or no?
Yes, sir.
Is it clear or not? I will explain one more time.
Yes.
Yes.
Sir, once more. Once
Once
more.
more. Okay. Till now, I think instead of weightage, we are using a distribution function. I think that is clear till now.
Yes, sir.
So what the distribution function tells you is how the particle is being distributed over here. Clear?
Yes,
Now,
sir.
if you consider a small area over here, let's say dx, and this is a function f of x. Now, if you multiply fx by dx, what will you get? The number of particle.
Yes, sir.
Yes or no? It will give you the
Yes,
number
sir.
of particles. So, if we consider the whole region, let's say in the total region, there are n number of particles. Clear?
Yes, sir.
Now, if we integrate over this whole area, will we get the total number of particles?
Yes, sir.
F of dx, will it give the total number of particles? Yes, no? I think it's clear
Yes, sir.
because this is a total number of particles. So that is what I meant, I wanted to say.
Okay, sir.
Now, by using a normalizing condition in this, what you can get, f of x is equals to n of px. So how did we get it? Can you derive this? No, derivation is also very simple. This much you know. Do you know this much?
Yes, sir.
Now what we can do is, can we simply write this? N is just a constant. So n integration of zero to L. Can we write this? Why we can write is, this is simply how much? 1. Can we simply write? Because this will again give you this total probability. I think we have written just above this normalizing condition. Understood? We have written this by hand. Mingma, Indira,
Yes, sir.
Is it clear? Can we write this? Can we multiply it
Yes, sir.
by this one? This times 1 we can write this, 1 we can write this. I think it's clear, no? I think now what we can do is we can put this C, this N in between. Now comparing this to what we can write. Is it clear now? Both have a same integration at same dx. Now this, whatever is sitting inside to be equal, this thing whatever is sitting inside should be equal that what we have simply written. Clear?
Yes, sir.
No, I think it's fine. We will do till here. Clear? Don't, wait. I have to take your attendance.